Okay, any questions with 3? Okay, number 4. Use the table of values on the right to estimate the below. Anytime you're using table of values, make sure that you do not use the b minus a over n for the width. Okay, I see that as a common thing. Some students try to force this into the problem, and it just messes with all your answer. There's already predetermined width that's going on, so we're going to just pull it from the table. We're not going to build it on our own. And also, this would be if we want the width to be all the same, like number 3. Okay, but in this case, we have to pull the width ourselves. So part A says use 3 middle rectangles from 1 to 15. So we're going to span across the entire subinterval. So one subinterval is going to go from 1 to 6, second subinterval from 6 to 11, third subinterval from 11 to 15. Every subinterval may not have the same width, but every subinterval will spread across the same number of order pairs. Now, there's a very specific way that I want you to draw your subinterval. Make sure you draw your subinterval starting from the middle of your first order pair to the middle of the last order pair of your subinterval. And then you're going to pick up from middle to middle, and then from middle to middle. Okay. Seems simple enough, right? But I see some students do this. They want to start at the end, and then this is just, I find that to be more confusing. You're not able to line everything up the way you would like to if you're going from here to here. So make sure you're starting in the middle of each order pair, so that you can make sure that there's a clear overlap between each of your subintervals. Okay, so then we're going to go from 1 to 6, 6 to 11, 11 to 15. When you subtract your endpoints of your x values, that will give you your width. So 6 minus 1 is 5. 11 minus 6 is 5. 15 minus 11 is 4. Okay. And then it's asking for 3 middle rectangles. So middle is in relation to the endpoints. Okay, we're not going to find the average. We're just going to, now 5 is not technically the midpoint between 1 and 6, but it is quote unquote the middle. It's between 1 and 6. So we're going to take whatever they give us. So we're going to go with the height from that 5, which is 2. So width times height, 5 times 2. That's the area of your first rectangle. Second rectangle, width of 5, height of 3, because 3 is the height coming from 8, and 8 is relatively in the middle between 6 and 11. And then third height, we're going to come from 13. So take the y value of 6, 4 times 6. Make sure that you're pulling your height information from the second row. I see students pulling the height information from the first row, and then that throws their answers off. So typically, I think table of values is relatively easy, but I see just a wide range of misinterpretations that can go on. So I understand all that. I'm trying to recall all the ones that I've seen over the years in hopes that you will be able to avoid them. Okay. All right, part B, 3 right-handed rectangles from 5 to 11. So we're starting at 5 going to 11. So we're just going to span across 2 order pairs, 5 to 6, 6 to 8, 8 to 11. Okay. Within each subinterval, you're going to pick off the right y value. So for the first subinterval, you're going to choose 7, because 7 is to the right of 2. So 1 times 7. Area of my first rectangle. Second rectangle, 2 times 3. Third rectangle, 3 times 1. Part C, use 4 trapezoids. make sure that you're using 4 trapezoid area formulas. We're not going to try to combine it. We're not going to double the heights in the middle. That's if every width is the same. In this case, we're not guaranteed that every width may be different. So we're going to have to go through our area formula for the trapezoid 4 different times. We can use this, or you could do 1/2 width, height 1 plus height 2. So we're going to spread across the interval from 6 to 15. So 6 to 8, 8 to 11, 11 to 13, 13 to 15. And then within each subinterval, subtract to get your width, and then your height, just the ones at the end. So in this case, I mean, there's only 2 to choose from. So, but just make sure that every trapezoid that you're only picking off 2 heights per area formula. So 7 plus 3 will be the heights of your first trapezoid. Second trapezoid has a width of 3 and heights of 3 and 1. Third trapezoid, 1/2 times 2 times 1 plus 6. Fourth trapezoid, 1/2 times 2 times 6 plus 5. Okay, I just thought of another one here. So if you can find any room, or if you can just use a separate sheet, I'm gonna try more. I'm gonna try this, call this 4D, using the same table. Let's do 2 trapezoids from 5 to 13. So 2 trapezoids from 5 to 13. We see that we can span across 3 order pairs. Subtract your ends to get your width. 8 minus 5 is 3. That's the distance between 5 and 8. 13 minus 8 is 5. Okay, we're gonna have to go through our area formula twice, each for each trapezoid. So 1/2 times the width, height 1 plus height 2. Notice that we're just going to pull the heights from the ends. So just 2 plus 3. We're not going to do 2 plus 7 plus 3. I see some students doing that. They want to add up all the heights. Only 2 heights associated per area. Okay, moving on to the second trapezoid. Width is 5, and the heights are 3 and 6. Okay, any questions with table of values, Riemann sums? Okay, let's do limit definition, number 5. Okay, so the formula will be given to you will look like this. So we can build that, right? All the width is b minus a over n. Your left endpoint is your a value. Okay, start off with your width formula. We're going to hold on to n because we don't want to limit the number of rectangles. Now start putting into our limit definition. It's going to be b minus a over n. So width is 1 minus a negative 1 over n, which is 2 over n. Right? We do b minus a. Okay, my a value is the left endpoint there, so negative 1. Okay, next up, we do want to multiply these together because this is width and height, but the height component is not quite in proper notation. Well, we have to get this out of function notation, so we have to involve the f and the function that we're dealing with. Okay. So I call this g of x here, but I'll just go back and say this is f of x just to, doesn't matter. And so to the side, we got to find a way to incorporate or this argument inside the expression. So I like to do this, rewrite the expression or the function without the x and the parentheses with the reserved space. So if you can do this, you know exactly where the argument's going to go. The argument's going to go inside those parentheses. Okay, so now this piece will replace this piece. I'm able to get this out of function notation. And if I have a width and height that's compatible, then I can begin multiplying and expanding. Okay, begin foiling this out here. I'm just going to focus on this portion. So the two middle terms is negative 2 over ni minus 2 over ni, and I just combine that to become minus 4 over ni's. Distribute the negative 2 through. 3 minus 2 is 1. Distribute the 2 over n through. So now I got to make sure I cleaned up everything involving with my height, and now I have to make sure I include the width because width is part of my component for area of the rectangle. We know that every term is going to get its own summation. So do that. And I want to separate the parts that are not associated with the summation rule. So I'll pull the 2 over n out, 16 over n squared out, and 16 over n squared. I'm sorry, n cubed, my bad. This is n times n squared. It should be n cubed. If I pull a 2 over n out, there's still a 1 sitting here. Okay, so now we can pick off the summation rules that's involved. Okay. Summation 1 is just n. Summation I is n times n plus 1 over 2. Summation I squared is n plus 1, 2n plus 1, all over 6. Every fraction should have matching degrees so that we can pull the fraction out of it. We talked about how, I mean, we could fold all this out, or we can just pull the most important information that will create the first term, and because we know everything else will be a lower degree. So 16 times 2 is 32, and there's 3 n's here, so 32 n cubed. There are terms of lower degrees, but we know that every fraction, we only care about the highest degree within each term. Okay, so we have matching degrees here. So we just take the coefficient, 2 over 1. Second fraction, limit as n approaching infinity. I find the highest degrees. The degrees match. I just take the ratio of the coefficients. Degrees match, ratio of the coefficients. Okay, so 2 plus 8 minus 32 over 6. Okay, let's go to the back page. Number 6. Okay, direction says to find the antiderivative, so I'm going to use the notation to indicate what I'm about to apply. But a couple of things we got to do before we do power rule, right? We got to resolve the parentheses, resolve the squared, make sure we take the time to FOIL out. So we'll take that 2x minus 1, write it out twice, distribute, expand that through first. So once I expand that through first, then I can worry about the x distributing through. Okay, so 2x minus 1 times 2x plus 1. Oh, sorry, my bad. Okay, so once we FOIL out 2x minus 1, Distribute the x through. And now we're ready, right? So no radicals in the denominator, no parentheses, no x's, no variables to multiply together, and nothing in the denominator. Okay, so apply power rule for each term. Add 1 to the exponent divided by that new exponent. X becomes x squared over 2. Don't forget about that plus c. Okay, number 7, same idea. We're taking the antiderivative, so I'm starting with my notation there, and I'm just going to clean up as I go along. So I see some radicals that I wanted to resolve. So this is x to the 1/3, but it's still out of place. So I'm going to push this x up to the top in the numerator, make it 4x to the negative 1/3. This square root of x is in the numerator. That's fine, but we do need to rewrite it as a rational exponent. So x to the 1/2, 3x squared. That's good to go. I'm going to wait until every term is ready. So I'm just going to copy that down. And the last term here, the x to the 4th comes up, but the 3 stays down. Okay, so we only care about bring up variables to the numerator. We don't have to worry about any coefficients. So I just push that coefficient out as 1/3, but I made sure to bring the x up to the top. Okay, so this is where we need to be before we can apply a power rule. Okay, so now the next step, we're ready to do power rule. Once you begin adding 1 to the exponent divided by the exponent, make sure you make your notations drop out. These two will go away. In place of it, you'll have a plus c, right? Just like number 6. As soon as you apply power rule, your notations go away. Okay, adding 1 to the exponent. Negative 1/3 plus 3 over 3 is 2/3, dividing by that same value. 1/2 plus 1 is 3/2, dividing by that same value. X squared becomes x cubed over 3. X to the negative 4th becomes x to the negative 3 over negative 3, and then plus c. If you see any messy denominator fractions, flip them up as the reciprocal. So 4 times 3/2. This is 2/3. This I can just reduce. I can just multiply those out. And in your answer, if there's any remaining negative exponents, bring them back down to the denominator, right? So those are the same things that we did first semester. A lot of carryover from first semester as well. Mhm. Yeah, you can leave it as a rational exponent, or you can bring it back as radical form. Either is fine. Okay, number 8. Now on my key, I presented the solutions a little differently, so I prefer to go through what I'm about to show you, splitting up in every fraction first. But I'm going to first rewrite it. As rational exponents. Okay. We have to split into individual fractions because this x is going to influence every term. And then once we split up, we can handle them individually. Now, all these denominators, it's nice to have 3 separate terms because we can handle them individually. They're each just a smaller problem to deal with. But we know that individually, the x is still all in the wrong places. We have to bring all the x's up. So we got to make sure we flip them to the top and change the sign of the exponent. Right, so the way that we merge these variables together is we're going to be subtracting or adding, quote unquote, or add or subtract exponents depending on what the sign is. So here, this is 3 minus 1/2. The same thing as 6/2 minus 1/2, which is 5/2. Notice that I'm keeping my notations all the way through because I haven't done any calculus yet. I'm just algebraically cleaning up just to get to that power rule point. 1/2 minus 1/2 is 0. X is 0, it's just 1, right? Doesn't make the 2 go away. It's just 2 times 1, which is 2. 1/4 minus 1/2, the same thing as 1/4 minus 2/4. Same thing as negative 1/4. All right, so now we're ready for power rule. Okay. So now we're going to add 1 to the exponent divided by the new exponent. So as soon as we take our next step, our integral in dx notation drops out. Five over 2 plus 2/2 is 7/2. What does 2 become? 2x, right? A constant doesn't go to a 0. A constant is going to rise up to a degree 1. Okay. Negative 1/4 plus 4/4 is 3/4. I'm going to flip all my denominator fractions up.
The denominator, you just like flip it.
That's right. Yeah. Dividing by a fraction is the same thing as multiplying by its reciprocal. Okay, let me go run through the steps for number 9 and 10. Okay, so first, I want to know I have to go through my antiderivative twice from f double prime to f prime to f of x. So to go from f double prime to f prime, I'm going to first set up my notation to indicate that I'm going to take the antiderivative of the expression in front of me. Once I do that, I know that will take my expression and make it rise up to the f prime level. Every term is nice and ready for power rule, so I'm going to go through power rule. For each term, the 1 becomes a 1x. Don't forget a plus c. So now that I have my f prime, I'm going to clean up and also prepare for my next step. I know I got to take the antiderivative again, and that will take this expression and make it rise up to the f of x level. So I'm going to go through power rule again, go through power rule, add 1 to the exponent, do that for every term. The x becomes x squared over 2. What does the c become? Cx. That's right. It's a constant, so it's like a 5. 5 becomes 5x, so c becomes cx. Now this process will produce its own constant, so we also need a plus k, or we can say plus c sub 2. Okay, those are the common ones. That's fine. And then just do some cleanup. So if you're asking for general expression from the second derivative level, you're going to have 2 constants, a cx and a k. Okay, finding a specific solution means that along the way, we're going to be looking for our constants before we move on to the next step. So in this case, same process as number 9, you're going to have a plus c show up. But then once you get that plus c to show up, you can resolve 1 and replace the f prime with a 9. And then if I algebraically add and clean that up, that will allow me to solve for c. In this case, c ends up being 0. So it looks like that just drops away. And then Really, so it's gonna be plus 0. So plus 0 just goes away. I take my antiderivative again. This time it's gonna produce a plus k. And then I can use my order pair at the function level to insert and find my k value. So 3 goes in for my y or f of x, 1 goes in for my x. Combine those like terms, k equals 1. So I'm able to write my function. So technically there's a plus 0x plus 1, but we know 0x just goes away. So that's why this doesn't produce anything for us to have for x. And then finally, make sure you know your trig derivatives, because from the trig derivatives can work backwards and to find all the trig integrals. So for instance, if I ask you, what is the integral of sine x plus 2 cosine x minus cosecant squared x dx? Okay, we go backwards, right? The integral of sine means I'm starting at the right side and moving left. What's the integral of sine? Negative cosine, right? Has to go right. I know that these are easy to mess up, to mix the signs up, because we're used to derivative rule, right? We're not thinking about antiderivative rules that produce a negative cosine of x. Okay, what does cosine produce? Wait, cosine produces a positive sign. Right, this is the antiderivative. This is not the derivative. This is the antiderivative. So understand that we're working backwards from the trig derivatives. Okay, and what does cosecant squared turn into? Negative negative. Yeah, negative cotangents, but there's a negative here as well, so we got to keep track of that. So careful with these, especially. These are easy for students to miss the signs up because we want to think it's derivative process, but it's the antiderivative process. All right, I'll leave the remaining time for any questions that you guys have. Mm-hmm. Find in between. I'll get them good today. Define the because you're doing 1 to 5 halves, you don't know how to say. So one, I really did one. It's the average of two numbers. So to find the average is just a plus b divided by 2, or you think of it as half of a plus b. So you just add these two numbers divided by 2, or add the two numbers multiplied by half. So 1 plus 5 halves, same thing as 2 halves plus 5 halves, which is 7 halves. 7 halves times 1 half. It's 7 fourths. So just add the two numbers divided by 2 to get the average.
So then, and then actually, it's not 5 over 2, like
Plus 4 divided by 2.
Or wait, you just saying.
On the right, on here.
It's because of these rules.
Yeah. So then you can.
Yeah.
Can you explain reading number 2?
I was like, why don't we do that? First of another.
2.
Yes.
I was about to be like.
In all the equations except for the trapezoid one and the derivative.
That's right, and the trig. Yeah. So for number 2, First thing to do is, okay,
How far am I?
this one's a little bit weird because it starts at 3
Is your?
on the, so I'll let you. In this case, we know it's gonna be, we know it's gonna be. Are you ready? I started off with the parts that are not changing, so the 7 is where the division sign, those aren't changing, so I'm gonna go ahead and put them in, let's get you over time. The 3, the 4, the 5, and 6 are all changing, I know that's gonna be involved in I. 27, 64, 125, 216, all involves I. Normally, I would let you start at I equals 1, but in this case, it's gonna be more convenient to start at I equals 3. Okay, so that means when I insert I equals 3, I'm gonna get this.
Right after this,
Yeah.
like.
So numerators. Produced.
She said you can't get it.
If you start like I equals 1, I did I plus 2.
You
That
can do
makes
that
sense.
too,
Okay.
yeah, but I'll make it easier on the quiz where you just start at 1 and not have to jump. Okay, now, the bottom here, we gotta be able to plug 3 into something that'll produce 27, 4 that'll produce 64, 5 that'll produce 125, and 6 that'll produce 260. Couple of things that you want to explore, it could be a multiplication thing, it could be something involving like a polynomial, I squared or I cubed or I cubed four, or it could be involving something.
We never did it. We never did it. Those are the.
So in this case, looks like it's gonna be 3 cubed, 4 cubed, 5 cubed, 6.
Honestly, with the boys right now, I think it's.
So that's gonna tell us I cubed.
I mean, it's but like.
And if you're unsure, you can just always, test your rule. If your rule will produce each of the terms that it's supposed to produce, you know you're good, you know you're sitting at the right answer. And then what's the last line? So it's a trial, it's a trial and error. Playing around with different relationships that will produce what you want, or what do we want and it's not. That makes sense.
No, on the quiz, do all the I one, right?
That's right, yeah. That's this is a little bit weird, I'll start at 1 of the.
Did you ever do it? No.
You got what?
Yes, I'm gonna ask you for, show me.
So you work until you.
Because it goes up to. I want to figure it out on my own. I don't want to tell me, but I also want to do it. So.
No, I don't figure it out. It's like when you start again, you put it, like, I'm finally good at it. It took me like 30-40%, but I got. And I was like, I'm gonna do that. I was like, but
It's gonna be like that. No, it'll be a thing value.
Okay, can I write it out? That, right? You're gonna simplify that. It's like, would it become like? Okay, I've seen it. They did like big game and so longer it's looking for have direction. I would just be there. I did it.
Yes, 1, 4, 15, 1 half.
They took up too much time.
Yeah, I know.
So I was like, I came in late. I came in at 7:30. You guys had just started. And I saw
Yeah, and I wanted to like do work before I came here.